Hi everyone! Today we are going to explore together another way to do classification using another machine learning method called naive Bayes classifier. So naive Bayes classifier belongs to the family of methods in machine learning called generative models. So we're going to talk about generative models, explain what's a naive Bayes classifier, the setting, provide an example, and I will show you how to estimate probabilities based on data. Before we dive in, let's first recall an important concept in probability called conditional probability. So conditional probability is the probability of an event happening given that another event happened. For example, suppose you have an event A, which is the event that you miss school, right? The event B being your clock didn't work in the morning, failed. So if you look at your past history, the probability of you missing school, which is probability of A, may be small, right? The probability of your clock failing may be also small. However, if you want to check the probability of A whenever B happened, we call it conditional probability of you miss school given that your clock has failed to work, right? So this can be written as the probability of you missing school and the alarm clock failed divided by the probability of the alarm clock failing. So you could expect that P of A would be small, right? P of B could be small. It's rare that you miss school. It's rare that your alarm clock fails. However, the probability of A given B could be much larger, okay? Because you probably would be missing school whenever you're not waking up in the morning. All right. So another way to write the conditional probability is by just doing the multiplication of these two terms here, and you have probability of the conjunction A and B is equal to P of A given B times P of B. So you see how this could be useful in many ways. So it's possible to write P of A intersect B just as we have seen before it's possible to write P of A intersect B this way. It's also possible to write P of A given B in terms of P of B given A times P of A by just applying the Bayes rule one more time, but this time instead of writing P of A given B, we would write P of B given A is P of B and A, which is also P of A and B similarly, and divided by P of A. So we could also do the product of these two and have the term written this way. So if we have P of A intersect, we are writing P of A and B in two ways. We could put these two terms in inequality, and in this case we are going to derive the rule that says probability of A given B is probability of B given A times probability of A divided by probability of B. This is what is known as the Bayes rule, a very useful rule in many applications. All right, so given this rule, what we call P of A is the prior. It's what we observe in the population, for example, for the event A to happen. P of A given B is called the posterior, which is the posterior distribution of A given that B is observed. P of B is called the evidence, right? And finally, P of B given A is called the likelihood. So this is, as I said, one of the most important formulas that actually exists in probability, and it is widely used in several applications. We're going to use it today to derive naive Bayes classifier. Before we use Bayes rule to derive naive Bayes classifier, let me first show you how useful this could be in practice. But first of all, let's write a table in which we give all possibilities of events A and B happening. Suppose we are just focusing on two events A and B. Whether A happened or not, we're going to call it A. If it didn't happen, we call it not A. The event B happening or not happening. So we're going to see at the intersections all possibilities of A and B happening or not happening. So for the intersection of A and B, we are going to talk about the probability of A and B happening. At the intersection of not A and B, we're going to talk about probability of not A and B happening, right? The lines, at the end of the line, we have what we called, and the columns, we have what we call the marginals. Probability of B happening is the probability of A and B happening plus the probability of not A and B happening, which means that B happening no matter whether A happened or not. Rewriting P of B as the sum, which is the marginal, as the sum of the line would be very useful because we're going to plug it into Bayes rule. So we have P of B and P of not A and B. So recall Bayes rule is P of A given B is rewritten as P of B given A times P of A, the prior, divided by P of B. So you can just plug in this value here, right? And then you could rewrite P of A intersect B using the conditional probability. not A intersects B, using again the conditional probability, which leads us to another formulation of Bayes' rule, which is the formula here. That actually, so you see, you recognize this is what we had before in Bayes' rule, but this one is now a little bit more detailed, like a lot more detailed, using the table that we just saw. So here's an example of using the new formulation of Bayes' rule in order to predict whether a patient has cancer, given that some lab test is positive. So we have some prior data about how effective was the lab test. And we're going to use the new formulation to estimate the probability of the patient having cancer, given that the patient had a positive lab test. This is something that is hard to estimate, but using different kind of probabilities as observed from prior observations, we could come up with an estimation of probability of having cancer, given that the lab test is positive. All right, so suppose that the incidence of cancer in the population is of 0.8%, which means that the probability of someone having cancer, which is the prior, which is in this case we call it the prior, is of 0.008. Okay, the probability of not having cancer in this case is the complementary. Recall one of the axioms of probability. Probability of the event A is simply 1 minus the probability of the event not A, right? Not A. All right, in this case, we could calculate the probability of not having cancer as 0.992. Suppose we have another piece of information that tells us how effective is this lab test to predict someone having cancer. In other words, the probability of the patient having a positive lab test, given that the patient truly had cancer. So this is, the test is, in this case, very good. It can predict that a patient had probability of patient having a positive test, given that the patient truly had cancer, is of 98%. Okay. Likewise, we calculate the probability of the lab test being negative, given that the patient had cancer, which would be the complementary of this value here. Okay. Suppose we have another piece of information that tells us about the false positive, the probability of the lab tests being positive, given that the patient did not have cancer. Those are the false positive. What actually the test is predicting is different from reality, right? So probability of having a positive lab test, given that the patient didn't have cancer, is of 0.03. Plug in all these pieces of information together using the new formulation of Bayes' rule. We get that the probability of the patient having cancer, given that his test was positive, is of 0.21. Okay, so you see how the Bayes' rule allowed us to flip the probabilities and use the information that we could observe, rather than to estimate a probability of an event that we couldn't observe. So now you must be wondering, why are we talking about probability and conditional probability and Bayes' rule? So let's recall first our setting for classification. So we're given some data. Data has labels. We have features. We have features. We have labels, right? And we want to learn a classification function that maps the features to the labels. All right. So we are learning this mapping, but in this case, what we are trying to accomplish is to learn this function, this mapping, not through a decision boundary like we did before, but through using probability, the conditional probability of the label y, given that what was observed in the data, which are the features. Before we show how we could find this mapping of this function based on the probability of y given x, I would like to clarify an important point in machine learning, which is the existence of two classes of algorithms. We talk about discriminative algorithms when we want to model the probability of y given x, which is the conditional distribution of the labels given the data, right? In discriminative algorithms, we aim to find a decision boundary that separates positives from negative examples. Recall that, so we did that in the previous lectures. To predict a new example, what we check is in which side does this data point, when you project it in the dimensional space, where is this data point located, on which side of the decision boundary? This helps us decide the label of the point, right? So what we are doing here implicitly is to calculate the probability of y given x. This is what we are modeling by finding such a decision boundary. In contrast, generative algorithms adopt a different approach. Instead of building one single model, which is a decision boundary, and use it to classify a point as positive or negative, what we are building in generative algorithms is two models. one model to what positive example look like, and one model, a different model, to what a negative example look like. To predict the class of a new example, we are going to match this example to the existing model, to the two models, and see which matches the best, right? So I'm modeling in this case the probability of the data given the label and the probability of the label. And we're going to use Bayes' rule in order to flip the probability, right? So in discriminative algorithms, we are modeling P of y given x. In this generative algorithms, we are going to model P of x given y, model P of y, and then use Bayes' rule in order to flip the probability and have an estimation of the probability of the label given the data observed. Okay, so how do we make a prediction? To make a prediction, we are going to use Bayes' rule and see which y maximizes the Bayes' rule. In other words, so we are going to use, so here's a function, argmax means that what is the y that actually maximizes the probability of y given x. So probability of y given x, we're going to use Bayes' rule and replace it in here, right? So I'm going to check what would be the y or the label, the positive or negative, that actually maximizes this quantity, probability of y given x. Okay? This could be just estimated as what? As the probability of just P of x given y times P of y. Okay, so we're going to estimate that by using this formulation here. This actually defines what's a naive Bayes classifier, which is a probabilistic model with really highly practical methods in practice, especially in natural language text documents, how to classify, for example, spams from non-spams, etc. It's naive because of the strong independence assumption that it makes, which is not realistic, but in practice this happens to work. It's a very simple model, very simple to implement, and however, it's a strong method that can be comparable to decision trees or neural networks or other kinds of algorithms. Okay, so here's the setting. So we dispose of data again. So we have data and labels. X is the feature vector and Y is the discrete label. We have D features and N examples. Example, consider document classification. Each example is a document. Each feature represents the presence or absence of a word, a particular word in the document. Okay, so we have our training set. A new example is with the feature values would be called, for example, X new would have the feature values A1, A2, AD for feature 1, feature D. And we want to predict the class or the label Y new for the example X new using the formulation of a naive Bayes classifier. Okay, so what we want to achieve is find the label of the new instance or the new example by looking at, so we have Y belongs to the set of possible outcomes or labels. So it could be +1 or -1 or 0, 1 or bananas and oranges, right? So what would be the Y that maximizes the quantity P of Y given A1, A2, AD, which is the values observed in the data. So what would be the probability of what would be the Y that maximizes the probability of Y given the data observed? So this is what we want to achieve. We want to find the label Y for new instance X. This label would be estimated by looking into the Y that maximizes this quantity, probability of the label Y given the data, right? So we're going to use, of course, Y in big Y, which is the possible labels, +1, -1, 0, 1, or even bananas and oranges, right? So what would be the Y that maximizes this quantity here? Okay, applying Bayes' rule means that we're going to just replace this formula by its corresponding Bayes' rule. And as we said before, this will be estimated by just looking at the probability of data given the label times probability of the label. So the question is, can we use this, the training data to estimate these two terms? The answer is, for P of Y, yes. We can easily estimate it by, if we have a very large set, we could estimate probability based on the frequency of Y happening. So we just count the frequency with which each label Y occurs in the training data. So how many yes you have, how many no you have, just like in the example we have seen before about hiring applicants. Okay, P of Y can be easily estimated from the data by counting the frequency of positive, let's say, and frequency of negative examples in the data. All right. However, the probability of A1 AD given Y is harder to estimate. Why? Unless we have really a very, very, very huge, large sample, it's very hard to find exactly the combinations of value A1, value A2, value AD happening given the label Y. So it's really, we need to see every example many times, every appearance of these combinations of feature values in the data, see it enough times to be able to estimate, to have an accurate estimate of its probability. So this is hard, and that's where the term naive is happening, which is that we need to make some assumption, and the assumption happens to be naive because we are going to assume that A1, A2, AD are independent given Y. So how are we going to estimate this probability of data given the label Y is by making some simplifying assumption.